So this video is part 3 of the chapter on covalent bonding, and this one is on sigma and pi bonding. We're going to need to know about pi bonding if the molecules has a double bond or a triple bond. So we need to know the two types of bonds that are possible. Sigma bonding involves an end-on overlap between orbitals. Pi bonding involves a sideways overlap of orbitals. You'll see it on the next slide here. Okay, so you have this end-on overlap means that these two are pointing, the ends of these two p orbitals are pointing towards each other, and that they're going to overlap over here. And when they overlap, then you have more of the electron cloud in the middle. Actually, if you see other drawings, it's a little bit larger because they add together because they're waves. And so this would be the covalent bond right here. And it's just this electron cloud or electron density that's concentrated along the line that connects the two nuclei. And those would be the sigma bonds. The pi bond, on the other hand, is below. And you look at p orbitals that are not along this axis right here, which in this slide they call it the x. This would be the x-axis. So instead, they're oriented along the y-axis or the z-axis. And when two p orbitals get together, they get close together. There's a type of bonding that occurs called pi bonding, and you get this sideways overlap between the two, and the sides just kind of blend together. So I like to draw a line, draw my py orbitals so that they're a little bit fatter, put two p orbitals close together, and this is actually a better picture of the sideways overlap. So this right here is the part that's common between them. Now that might be the reality, but no one ever writes it that way. Instead, you put them farther apart and then make these curved lines. So what I've drawn right here is one pi bond, which is the same as this, one pi bond. So you can blur them together the way it is in this drawing here, where you've got the red, or you could, when you're drawing molecules, and it's easier sometimes to do it that way. You'll see what I mean. Okay. So then we're going to go through 4 molecules. This is the first one, C2H4. The procedure here is first to do the Lewis structure, then the Vesper structure. From the Vesper structure, you can get the bond angles and the type of hybridization. Then you want to work out the orbital diagram for the hybridization, and you want to work in to the orbital diagram. You want to work in the orbitals that are going to be used for sigma and those that will be used for pi bonding. So it takes a little bit of time here. It's okay to go through it all. So C2H4, the Lewis structure first. If you go through the details, we've done this before, that's going to be the Lewis structure. The Vesper structure, you have three groups of electrons for each carbon, 1, 2, 3. So that's 120-degree angles. That's the planar triangular geometry, and it's going to be sp2 hybridization. And maybe you have memorized that 120 degrees means sp2 hybridization. So 120 degrees all the way around here. So it's going to be sp2 hybrids. And what's new here is that it will be for the sigma framework. Okay, there. Move that over. And then that will involve three electrons per carbon. Okay, so sp2 hybrids, and the bond angle is 120 degrees. The next step is to draw the hybrid orbitals, the sp2s. So go back to the framework of the molecule. Remember, each sp2 hybrid is this almond-shaped orbital. The little nub on the other end of it is not shown. So those are sp2s, 120 degrees. Then there is a second set for this carbon. Then you can put the hydrogens in. You can call them s orbitals, or you can label them H for hydrogen. This is your sigma framework. And you can label sigma bond. Sigma bond, this is the end-on overlap. Sigma and sigma. All right, now let's look at the orbital diagram before we go any further. So look at one of the carbons. Carbon has 6 electrons. 4 of them are in the valence shell. 2s, 2p, 1, 2, 3, 4 for the valence shell. Okay, now you're going to hybridize here, and you know what you got to do. So first thing would be to, in other words, because you know the structure, you have already looked at the sigma framework, you know how this has got to work out. So set it up that way. Okay, first thing you want to do is promote one of the electrons out of the 2s. 1, 2, 3, 4. Then you're going to make 3 sp2 hybrids from an s and 2 p's. So the next step is 1, 2, 3 sp2 hybrids. You have 1 p left over, and notice that I've taken off the 2 here. I think I mentioned that in another video. That's fine to do that. I always do that, in fact. So then you have 1, 2, 3 for the sp2 hybridization, and then here's what's new here. You have a p electron that is unhybridized. That's the one that will be involved in the pi bond. All right, so now we can go back and redraw just the stick diagram rather than putting all this stuff in here. It's kind of complicated when you want to focus on the P part of it. So let me do that first. So I'm going to redraw the sigma framework. We've got the bond angles right and the number of bonds and so on. All right, now we're going to focus on the unhybridized P, which is this one, on the first carbon, and then you've got an unhybridized P on the second one as well. So they will do that sideways overlap, and then you're going to end up with a sigma here, and this one is pi. So you could end it here, or you could go back and, if you wanted to, superimpose the p's here and show the whole thing. That's fine as well. But also, I didn't mention it, there's a rule that you want to think about. So whenever there is a double bond that's made up of 1 sigma and 1 pi bond, if there's a triple bond, this is made up of 1 sigma and 2 pi's. All right, and so whenever you see a double bond, you know that it's going to be exactly what we see here, 1 sigma and 1 pi. So that's this type, and with triple, we'll get to that as the next example. All right, let's have a look at the figures from Pearson here, publisher. And let's start up here. This is the sigma framework in purple, right? 120 degrees. The unhybridized P's are here. They haven't overlapped yet, but they're sitting right there. In the second part of this, okay, they've added the hydrogens in blue. That's all. Okay, the third part of this is where they put it all together. And let's go over it. So you got the purple is the sp2 hybridization for each of the carbons. The blue is the bonds to hydrogen. And then they've taken these unhybridized P's, they've done the sideways overlap. And so that's what the pi bond looks like. The two together, one sigma and one pi, makes the double bond. Okay. All right, our next example is on the next page. So formaldehyde is second example here, and first we want to start with the Lewis structure. And that's going to be oxygen, carbon, hydrogen, hydrogen. And if you go through the Lewis structure, you're going to come up with a double bond and two lone pairs. Okay, so that's Lewis. You've determined from this step that you got single bonds and double bonds and lone pairs. The Vesper structure is based on the idea that the carbon has 1, 2, 3 groups of electrons, and then the oxygen has 1, 2, 3 groups of electrons. So 3 groups means sp2 hybridization, and you can think here, this is 120 degree angles, sp2 hybridization for oxygen, and then similarly for carbon, there are 1, 2, 3 groups of electrons. So this is the Vesper, PR structure. And I'll put some bond angles in there. 120 degrees going around. And also this one, I don't know, you can put in 120 degrees there as well. It is, but it's very, very different from that of the carbon. So the oxygen will have sp2 hybridization. The carbon will have sp2 hybridization because of the planar triangular geometry there. Okay, and I think that's it for the Vesper structure. Next step is to, you could draw the sigma framework, or you could, yeah, let's go ahead and draw the sigma framework. You can do it either way, but sometimes it's better to have a vision of where you're headed before you get there. Okay, so the carbon has 1, 2, 3, and by the way, I didn't mention that since there's a double bond here, it's 1 sigma and 1 pi. So keep that in mind as well. All right, then the oxygen has 1, 2, 3, and then you get the hydrogens here and here. So these are sp2s. And you have lone pairs here. Okay, that would be the sigma framework. Those hydrogens are a little bit big, but I think I drew them just a little bit too far away from the orbitals. Okay, so then you could continue along. You could draw the stick. Let's go ahead and do the orbital diagram next. You know that you're going to need to include these unhybridized P's. So let's see how the orbital diagram looks like to see if that's true. Okay, so for carbon, the valence shell has 4 electrons. And because we need that unhybridized P, put it there. Okay, and then we know we're making sp2 hybrids, and then there'll be an unhybridized P. So 1, 2, 3 sp2 hybrids, and 1 P, 1, 2, 3, 4. All right, now for oxygen, this is for carbon. Next is oxygen. So oxygen has 6 electrons in the valence shell. And take one of these, move it, I guess, over here. So you're going to get 2s, 2p, 1, 2, 3, 4, 5, 6. Then you're going to hybridize an S and 2 P's. And then you're going to have the unhybridized P left over to make the pi bond. So it'll be 1, 2, 3 sp2 hybrids. And the unhybridized P, 1, 2, 3, 4, 5, 6. And here, this is for the lone pairs. This one is for the sigma bond, and this one is for the pi bond. And this one here is for the pi bond, and these 3 are for the sigma bonds. Okay, so now you got it diagrammed, and then go back and we can just draw the stick figure: carbon, hydrogen, hydrogen, oxygen, and the lone pairs. So this would be a simpler depiction of the sigma framework. Now what we want to do is look at the one unhybridized P on the oxygen, the unhybridized P on the carbon, let them sideways overlap, so you have a sigma and a pi, which makes the double bond. That's pretty much the all of it, I suppose. And then this looks kind of funny. This depiction on this slide is a summary of what we just did. So for the carbon, it's sp2, sp2, sp2. Oxygen, sp2, sp2, sp2. You got your lone pairs. End-on overlap to make a sigma bond. Sigma bonds here and here with the hydrogens. Then you have the unhybridized P's that do the sideways overlap to make the pi. And that would be it. That's what it looks like. Okay, next example is C2H4. And this one has, because it's linear, the Lewis structure looks the same as the Vesper structure. Here we see that the hydrogen carbon bond, our angle is 180, and then the carbon hydrogen is 180 as well. So it's linear. And each carbon needs 2 sp hybrid orbitals. That's what we need. And also triple bond, 1 sigma and 2 pi. Okay, so that's what we need. Okay, then start with carbon, 2s, 2p, 1, 2, 3, 4. Definitely promote one over there. For hybridization, a 2s and a 2p. So 2 atomic orbitals will combine to make 2 hybrid orbitals, 2 sp hybrid orbitals, and then there will be 2 unhybridized p orbitals. So you do that twice, one for each carbon. And next you want to draw, I did it the opposite for the other ones. First I drew the sigma framework and then I did the orbital diagram, but you really can do it either way. So then here are the 2 carbons, and you have 2 sps for each carbon. And on overlap, to make a sigma bond, then you get the hydrogens, sigma and sigma. So that's the sigma framework. Now you want to do the pi on top of all of that. So it would be, that's the sigma framework. All right, this one's interesting. So you have an unhybridized p on the first carbon interacting with an unhybridized p on the second one. So you got a sigma, this one is a pi, and then you've got another one, since there's 2 unhybridized p's, and right now the blue and the black, they're in the plane here. So you got this and that is the plane of the whiteboard. But now we want to add in orbitals that are perpendicular. So you kind of draw them on an angle, but they're supposed to be actually coming in and out of the plane of the board, like that. Maybe fill them in so you can really see their differences with everything else there. Sideways overlap again. So there's a second pi bond that is perpendicular to the first. And then the last thing that happens is these 2 pi bonds kind of blend together and kind of form a cylinder where it's just all the way around to the back and everything. So that, in other words, they just start to circle around. The electrons just circle around in a cylinder around this sigma framework. So that's kind of an odd thing, but definitely shown to be true. It's the way it works. Okay, so this is C2H2, and it starts here with the let's see, these are the sp hybrids for the 2 carbons. You got the 2 unhybridized p's. See, they do a better job. This is the one that's coming in and out of the plane of the board there. Okay, and then next is the bonding out to the hydrogens in blue. And then the third picture here, you've got bonding to hydrogen. So this is a sigma bond, that's a sigma bond. You got a sigma bond in the purple. So this is much better looking than what I drew. So you got 1 pi bond that's in the plane, and then another one that's perpendicular like that. And they don't show it, but some books do. This all just kind of blends together, and it's just one big cylinder of pink pi bonds. Okay, and let's see what else we got here. Oh, benzene. Forgot about that one. Okay, this is the last one, but this is long. C6H6, this it's known to be a ring compound, so you got a ring of 6 carbons. And if you did the Lewis structure, you'd come up with the same thing as the Vesper structure. So C6, H6. All right, and then you've got unhybridized P. So in other words, each carbon has 4. So this is so far it's 1, 2, 3, but each carbon has 4 electrons in the valence shell. So the other one is an unhybridized P. Each carbon has 1. You can think of these as being above and below the plane, and they actually bond to make pi bonds, sideways overlap. So I'm going all the way through this just to give you kind of before we get into the details here, just a picture of it. So then you get alternating single and double bonds. All right, now there's another equivalent structure where the double bonds are in the other place. So in other words, you got bonding here, here, and here instead of the way it was done with the blue. So you've got then another possible structure here. Where the double bonds are on, they're alternating, but they're on opposite, the other carbons. All right, so these two interchange with each other. And you could think of it as a resonance, I suppose. A little bit different, but you could think of it as a resonance. All right, so a lot going on here. Let's analyze it a little bit more. There is the sigma framework. You don't have to keep doing the two structures, but oftentimes you see it like that. All right, I redrew it because I wanted to emphasize the fact that these bond angles are 120. So 120 degrees, and that is all the way around, and that's the same for each carbon. So we're talking about sp2 hybridization, planar triangular geometry for the sigma framework. And then I think I can show you on the next slide. I got a lot of different pictures here, so let's look at this. On the top, these are the two, they're called Kekulé structures. Kekulé was a scientist who was just trying to work out the structure of benzene many years ago. And he just couldn't figure it out. He knew it was C6H6, but was always thinking of it in terms of a linear structure. And that would mean it would have to have triple bonds and single bonds and double bonds, so it was confusing to him. And he had a dream, so he was obsessed with it. And he had a dream, and when he woke up, he had dreamt about snakes going in circles. And then he realized that the only way you could explain all the information on benzene was that it was a ring structure with alternating single and double bonds. So that was kind of the beginning of the story of benzene. And then what we have on this the left-hand side here is the sigma framework. Okay, it's better than how I drew it. But then you can bring in the unhybridized P's, and you get a little bit of a perspective of it from the hexagon. So that's perpendicular to the plane of the hexagon. And then what else is down here? Oh, I love this diagram. I found this online. Look at that. Okay, so you got the orange is the sp2 sigma framework. So it's 1, 2, 3 for each carbon. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. So it's a little skewed for the diagram to give you a three-dimensional picture, but of course you get the 120-degree angles there. Then you have your unhybridized P's that are going to overlap. The fact that they're red on top of the circle and blue underneath gives you the sense that how they're going to combine. So you get the top halves of the P's are above the ring. The bottom halves of the P's in blue are below the ring. And that was the last one, was it? Like that. Okay, so then this is a different figure here. Nice, but not as nice as the last one. This one puts the hexagon on a little bit of a skew to give it some perspective. There's your sp2 hybrids, right? And then your P's are above and below. And what I mentioned before, excuse me, that's why I put this one up, because the top half of the P's come together and make a ring, and then the bottom half of the P's come together and make a ring. And this has been shown experimentally to be the case, so it's known that that's the situation. This is the simple depiction of benzene, and turn that one back, yeah. Okay, and so you can see why, perhaps. So the hydrogens are not drawn, they're just assumed. You've got carbon in each one of these corners here. So you get your 6 carbons. And instead of having the alternating double and single bonds, the circle is given to indicate that the P, there are 6 P electrons, and they all come together and form this ring of pi. So organic chemists use this symbolism, and everybody knows what it means. And you could start with one benzene ring. Let me try that again. And then oftentimes with molecules, you'll see a second one. That one is called naphthalene. If you have a third one, that's called anthracene. And then they just keep going. Plus, you can have, you can have another one up here. These molecules exist. And then over here, maybe you have a carboxylate group that would make it an acid. Sometimes you got alcohol groups like this. Just giving you some fun things to think about for when you finally move into OChem. But it's all based on the work that we've done with this course, the end part of this course. All right, anyway, I believe that's the last slide, so we'll stop here. I did not draw the sigma and pi orbital diagram. If I were to do that, hold on. If I were to do that, my N would be sp2 hybrids and one unhybridized P. That would be the end result. So this part, you have your 3 sp2 hybrids 120 degrees apart, and then each carbon has a P that enters into the ring. All right, that's the end here, and the end of the chapter as well. We'll move on to completely different topics now, but hope you've learned a few things about structures of molecules and how they bond, what the bonding is in the molecules.